In section 5.1, we will discuss in addition and subtractions of integer numbers. We did discuss already addition and subtraction for whole numbers, but now we're going to introduce negative numbers or opposites of positive whole numbers. So we're going to talk about the set of integers. So first, the set of numbers, and in this book, I know it's a little bit unusual notation, but the opposite to a number, so -1 will be denoted with this minus in the upper index. Okay, so we're going to talk about -1 like this instead of what we're used to as a regular minus, just because this will emphasize more what this really stands for. It stands for the opposite to 1. Okay, so in general, if you have a number line and if you say put, I'm going to do 2, the opposite of 2 will be on the opposite side of the 0 on the number line, and we're going to denote it with minus elevated. That's how they do it in this textbook. Okay, so that is the opposite, okay, to 2, and or we call it -2. Okay, so then the set of integer, it's gonna contain whole numbers. So which whole numbers, remember, mean 0 and positive here integers, 1, 2, 3, 4, 5, and so on. And also their opposites, so -1, -2, -3, -4. This is the set of integers, which consists of positive whole numbers, 1, 2, 3, 4, and so on, 0, and the opposites to the positive whole numbers. So remember this set, 0 and positive integers, this is the set of whole numbers, right? But add to it opposites, and you're having the set of integers. Okay. So let's find each of the following. For each of the following, find the opposite of x. So here, if x is 3, right? What's the opposite to it, right? And always think of the number line. So what's minus x if x is 3? Of course, it's most of us see it's going to be -3. If this is 3, then the opposite will be right here. So that's going to be -3. Okay. But what if x is -5? What's going to be the opposite to it, right? So now your x is -5. So the opposite to it, it means we need to bring it to the other side of 0. So it's going to be +5. So now the opposite to x will be +5, right? Because again, opposite brings it to the other side of 0, right? Within the same distance, but on the other side. So notice that I want to emphasize here one thing, that the minus x does not necessarily mean that the number is negative, right? Here, minus x is 5 because x was -5, right? So minus x just means the opposite to x, which can be both positive and negative, depending whether x we started with was negative or positive, right? And what's the opposite to 0? Well, if that's 0, right, the opposite to it is the same, 0. And so the opposite to x, in this case, is the same as the x itself, but that's only possible for 0. So the opposite equals the number itself only in a special case, when the number x is 0. Okay, so I think that's pretty straightforward. Let's look at the models of addition of integers. So we're going to talk about a few models. The first one is CHIP, or charged field model for addition. And here in the chip model, we're going to use positive integers will be represented by yellow chips and negative by red chips. And here notice that I put plus, or in the textbook they put pluses inside yellow chips just to remind those chips stand for positive numbers, positive integers, and red for negative. Or sometimes you might skip drawing chips altogether, but again at school you might just give yellow chips and tell kids this represents positive numbers and red ones represent negative, so you wouldn't necessarily see the plus minus signs on top of them. I will often use just plus minus. I won't even bother to draw chips around them and color them, but letting you know that that might be done also using chips instead of signs plus minus. So when we use just plus minus, that would be charged field model, which is similar to the chip model, except in the chip model you use chips, right? Okay, so for example, when you look at number 2, right, it's a positive 2, so you could represent it with 2 yellow chips. Or if you won't bother with chips, with 2 pluses, right? Now, the same 2 can be represented this way because the negative and positive chips or charges neutralize each other. So this minus and this plus here just kind of like cancel each other out. So this is still positive 2. The same positive 2 can be represented this way because here 2 negative charges will cancel 2 positive charges. So what really you're left with are 2 positive charges or 2 yellow chips, which is still the same. So now this positive 2 here can be represented many different ways, as long as after negative and positive neutralize each other, as long as after that you're left with 2 positive charges or 2 yellow chips, then that still represents 2. Same thing, negative 2, you represent with whether you just put minuses or you use red chips. The point being is there's many different ways to represent negative 2 because here positive and negative charges neutralize each other. So if what's left it's still 2 negatives, then that's negative 2. Right here they have 2 pluses, so they will cancel out with 2 minuses. But what you're left with will be still 2 minuses, so that's still negative 2 and so on. Okay, so how we're going to represent addition, we're going to work on that in a minute. Say I want to represent what is negative 4 plus 3. So I put 4 minuses or 4 red chips and then 3 pluses or 3 yellow chips. And then since minuses and pluses neutralize each other, what I'm left with is 1 negative charge. So that's going to be minus 1 would be the answer, right? Okay. So demonstrate each of the following additions using the charged field or chip model. For simplicity, I'm going to use charged field, so I don't have to draw yellow and red chips. Again, yellow stands for pluses and red for minuses. So here we have plus 5, so positive 5 plus negative 3. So to represent positive 5, I'm going to draw 5 pluses. And then I want to add to it negative 3, so that stands for 3 minuses, right? And then I see that the minus and 3 minuses and 3 pluses will neutralize each other, will cancel out, so I'll be left with 2 pluses, right? So the positive 2 is the answer to that, right? Addition. What about negative 2 plus 3? So here I'm going to put 2 minuses and 3 pluses, right? And since minuses and pluses neutralize each other, I'm going to be left with 1 plus. So the answer to it is positive 1. 3 minus 3 plus 2, so 3 minuses and 2 pluses. But of course, after minuses and pluses neutralize each other, right? 2 minuses neutralize 2 pluses, so you're left with 1 minus, so you're left with -1. And here -3 plus -2, so you have 3 minuses, and add to it 2 minuses, so really nothing gets neutralized, so what you're left with is 5 minuses, so -5. Okay, so this is the chip model or charged field model to demonstrate addition. Now we also have number line model for addition, and I want to remind you that you always start at 0, and imagine standing here. You always face initially in the opposite direction, so imagine facing that way, right? So whenever a number is negative, you're gonna walk backwards that many units. And whenever you're adding a positive number, then you're gonna go forward, right? So here, right, we're facing east. And if you want to write -3 plus -5, so that first -3 means you're gonna walk 3 units to the left, starting from 0, right? So this is the blue line here. And then plus -5, again, you're gonna walk this 5 units to the right, from where you are at this point. So from where you are here now, still you're facing east, right? And then you're walking backwards 5 units more. So altogether you ended up walking 8 units backwards, right? So the solution of this is -8, where you end up being, right, at the end of this transition. Okay, so that's the point when you start by imagine standing and facing east, right here, the positive number line. Whenever number is positive, you move forward. Whenever number is negative, you move backwards. And you illustrate it by drawing arrows of movement. So here 5 plus -3, let's demonstrate that. So first I'm gonna draw 0, 1, 2, 3, 4, 5. Okay, so I will go 5 units to the right. So remember, I'm facing to the east, so I'm gonna go 5 is positive, so I'm going 5 units to the right, east, forward. And then, so right now you're standing here, still facing, still facing east. So here's where you look. And then plus -3, so that means that you're going to be walking backwards, 3 units. So from that point on, you go 1, 2, 3 units backwards. Okay, so that's gonna put you here, right? So that stands for -3. So the distance ultimate, so now you're here, so the distance from 0 you actually traveled, let me maybe use different color like orange. So distance you actually traveled from 0, you're 2, right? 2 miles or 2 units east, so the solution of that is 2 plus +2. That's where you are at this point, right? If you imagine again walking 3 units backwards, that puts you at the 2 units to the east, so that's 2. Okay, so let's do -2 plus 3. So here is somewhere 0, and now you're gonna go. First, you're starting by facing east, right? Looking this way. This is your vision. But first number is -2, which means you're gonna go 2 units west, backwards, right? And then from that point on, so you're right now here, then you're gonna go So you went backwards, so you're still facing east, right? So then you're gonna go 3 units forward. Okay. So that will bring you to 1 number, right? When you go 3 units forward. So where you are at this point would be here. So you're at number 1, positive 1. Okay, negative 3 plus 2. So this time you start at 0 facing east again, and you're gonna start going 3 units backwards, right? And then 2 units forward. So that brings you to negative 1. Okay. And final one is pretty simple number line concept. You start at 0. First number is negative 3, so you're gonna have to go 3 units. You start at 0 facing east. You're gonna have to go 3 units backwards. And then, so you're here. And then another 2 units backwards, because the next number is negative as well. So that's minus 3. This is minus 2. So combined, of course, you're at, combined you went 5 units to the left, right? So combined you are at negative 5. That's where you end up being. Okay, so let's look now at the concept of absolute value. Absolute value of 4 and negative 4, right, which are opposites, will be the same because the absolute value represents the distance of the number to 0. Okay, so if you think of the negative 4 and positive 4, their distance to 0 is the same. They're 4, and that's going to be their absolute value. Okay, so the general definition here, and that's very confusing for students, is as follows. What if absolute value of x is x, if x is already non-negative? So what it means is, if your x, let me draw the case 1. Oh, that's very not straight. If this is 0, and if your x is somewhere on the right side of 0, then that x, the distance to 0, right, x is positive, so the distance to 0 is x as well, right? So for example, if x was 5, that's its distance to 0, right? So that's why the absolute value of x, which represents the distance, is actually the same as x itself, okay? Because x to begin with was positive. But now imagine x being to negative. So I write x, but x can hide inside negative number, can represent negative number, right? So for example, x could be negative 5. Okay, then you cannot say that this distance to 0, you cannot say that this distance is x, because distance cannot be negative 5. Distance cannot be negative. So what's the absolute value of x? Well, the opposite to that, because you want to make sure the opposite of that, if x is negative, minus x is positive. Okay. And this is written here, and this is what confuses a lot of people. But again, if x that we're starting with is negative, then minus x really means positive. So for example, if my x is, again, I'm going to use the same example, negative 5, then minus x is positive 5. It's opposite, right? That's why absolute value of x, which is negative 5, will be 5. Because minus x just means the opposite to x, right? So if x is negative 5, the opposite to it is positive 5, and that's what the absolute value is, right? Okay, so I'm going to practice that with you on question 5. And question 4 is pretty simple because, again, if the number is negative inside, the absolute value produces its opposite, which is 5. And the number inside is to begin with positive, the absolute value just produces that number because absolute value measures the distance of the number to 0. Here, notice that we keep minus in front, and now let's figure out what the absolute value of this is, right? The absolute value of negative 5 will be 5 because the distance of negative 5 to 0 is 5, but the minus that was in front remains, so the answer is negative 5. And here, again, this minus being in front of the absolute value remains. And what's the absolute value of 5? Well, it's 5. The distance of 5 to 0 is 5, and minus remains. Okay, and let's look at this. This one is tricky, and it boils down to understanding what is x, absolute value of x, if we know whether x is positive or negative. Okay, so first thing first, let's read correctly what this means. If the inequality symbol opens towards 0, that means 0 is bigger, x is smaller, meaning x is less than 0. So here means x is negative or 0. Okay. So if x is negative, the absolute value of x cannot be equal to x. Remember, x is negative. For example, negative 5. Absolute value of negative 5 cannot be negative 5. The same x, right? If x is negative, the absolute value must be its opposite, because the opposite to the negative number will be positive, right? So since x was to begin with negative, absolute value makes it positive. So I always, another trick to keep in mind, think this way: if x is positive, your absolute value remains the same, right? But if x is negative, if that's your x is negative, I didn't write negative x. If x, it's negative, then here will be your minus x, and that's going to be your absolute value. Okay. So that's the story here. Since x was negative, the absolute value cannot produce the x negative number. It will produce its opposite, minus x. And here, therefore, this is minus x plus x. Okay. And what's minus x plus x? Well, we can use the charged field model or number line to visualize it. If I walk x units backwards and then the x units forward, I'm back at 0, right? So that's 0. When you add number to its opposite, you're going to end up with 0. Okay, what about this one? Again, x is negative. Inequality symbol opens towards 0. That means x is to the left side of 0, meaning x is negative. Whenever that happens, the absolute value of x produces its opposite, which is positive. So here's the case. If x is negative, then minus x is positive. And remember, absolute value needs to produce positive number. So in that case, minus absolute value of x plus x will be, well, absolute value of x, as we mentioned above, will be minus x. Because now, remember, this one is positive because x was negative. But then what's the opposite to opposite? Right? If x is negative, minus x is positive, and then you're taking opposite to minus x, then you're back at x, right? So two minuses kind of cancel out because you're reflecting across 0 twice, right? You add again x to it, then 2x is the answer, right? X plus x, right? You would have x negative charges because x is negative, and another x negative charges, so twice x, which is negative, would be your answer. Okay, and here x is positive. Inequality opens towards x. If x is positive, then the absolute value of x is just x. You don't have to end up produce the opposite to it, because you remember absolute value needs to produce a positive number, and x is to begin with positive. So that means if the absolute value of x is just x, well, keeping in mind that this minus I have to keep, absolute value of x is just x, so now that's 0. Okay. Okay, and I'm gonna list kind of the definition, algebraic definition. Let's say once we use the charged field slash chip model or the number line model, we can devise those rules for dealing with adding integer numbers. So first, of course, obviously we know that when you add 0 to any integer, it's the integer m stays the same, right? So m plus 0, which is the same as 0 plus m, because addition is commutative, it's the same as m. But now, what about if the two numbers, you're dealing with two numbers, both non-negative, so positive or 0? Notice that inequality symbol opens towards the number, the symbols m and n, which means both of them are to the right side of 0. So if the numbers are already positive, then m plus n is defined like you use whole, those numbers are whole numbers, so we're adding whole numbers the way we learned in the previous chapters, right? Now, if two numbers again are positive, so and you're adding minus n plus minus n, then the solution would be minus m plus n. So again, you can add m plus n using whole number addition, because both m and n are whole numbers, they're non-negative integers, and then you carry the minus. Okay, and if you're adding one number n is positive, and you know m is bigger or equal to n, then when you're adding them, you really can write it as a subtraction, m minus n, and m is bigger or equal than n, so you're back at whole number subtractions, and similarly the other way around. Okay, but those rules seem complicated. We know most of them, so really the way you would describe it to kids would be the following. To add two integers with the same sign, add the absolute value of the integers and then keep the sum of those numbers, right? So example. So adding into two integers of the same sign. So obviously 5 plus 3 will be 8. Both numbers are positive. But what about negative 5 plus negative 3? Well, you add absolute values. The absolute value of negative 5 is 5. Absolute value of negative 3 is 3. So you're really adding their absolute values, right? 5 plus 3. And you're keeping minus in front of it. So this is this rule C here. Okay. So in other words, saying you ignore the minus, you're adding 5 plus 3, but really that means you're adding their absolute values, and then you carry the sign that both numbers had. So you carry down this negative sign. Okay. Now, to add two integers with different signs, subtract the lesser absolute value from the greater one, and then the sum has the same sign as the integer with the greater absolute value. Okay, let's analyze that. So what if you add negative 5 plus 3? So first, what's the absolute value of negative 5? 5. What's the absolute value of 3? 3. Which is a greater absolute value? That of negative 5. So that means from the bigger one, you subtract smaller absolute value. And the sign carries from 5, and the sign of 5 was negative, right? Because that was the number that ended up having bigger absolute value. So that's why the sign is, the sum remains is the same as of the number with the greater absolute value. So in this case, the sign is negative. The greater absolute value was of negative 5. So we really perform subtraction. 5 minus 3, and the sign was carried down from negative 5. Or what if we had to do positive 5 plus negative 3? So now the absolute value of positive 5 is 5. The absolute value of negative 3 is 3. Which one is bigger? Again, that one. So again, from bigger, you subtract smaller, and then the sign will be positive, right? Because this number had a bigger absolute value, right? Earlier, we had the negative. So those are the rules. One more time. If you're adding two numbers with the same sign, then you're adding their absolute values, and you carry the same sign that both of the numbers had, right? Now, if the numbers have opposite signs, you really are subtracting their absolute values, but the sign goes from the bigger number, the number with the bigger absolute value. So in this case, here was the sign was negative because absolute value of negative 5 was bigger. Okay, let's do a few more additions to remind those rules if we're rusty a little bit on that. So let's do 7 plus negative 3. Numbers have opposite signs, so I really subtract 7 minus 3. And now the question will be, will I carry the sign from, will the sign be positive or negative? Well, 7 in the absolute value is bigger than absolute value of negative 3, right? So the sign will remain positive. So I don't have to here add any sign, so that's going to be 4. What about negative 4 plus negative 9? Both numbers are negative, so I'm really going to add their absolute values and keep the negative sign. So that's going to be negative 13. Okay, now 5 plus negative 12. Okay, numbers have opposite signs, so I'm going to be subtracting 12 minus 5. And since 12, right, is bigger number than 5, then the sign comes from 12, right? So negative. So negative 7. And let's say negative 15 plus negative 2. Both numbers have the same signs, so I'm really adding their absolute values and keeping the signs both numbers had, so negative 17. Okay, I'm not going to go through that, but I want to mention that we have the same rules we had for addition of whole numbers. So closure property, whenever you add two integer numbers, the solution is an integer number as well. You have commutative property, you mean the order and the addition doesn't matter. A plus B is the same as B plus A. You have associative property, so when you have three numbers you have to add, you can group them any two neighboring numbers the way you want. So you can first add A with B and then to that C, or you can first add B with C and then to that A. In fact, if you combine again those two rules, it turns out you can add however any pair first, because you can also switch the order B with C, right, and group however you want. So in fact, you could also add A with C first and then B, because that's a combination of associative and commutative. Then you also have identity property, which means identity is 0 here. It's that element that when added to A doesn't change it, it's still A. And then every now number that's a new, we didn't have it for whole numbers because we couldn't talk about additive inverses. So the opposite to a number, we can also call it additive inverse of A, because when you add A to its opposite, it produces 0. That's why sometimes this negative A is called additive inverse, because adding A to negative A produces 0. Okay, I wanted to do something here. I don't know, it's the order is scrambled a little bit. I'm gonna do additive inverses first. So let's find additive inverse of each of the following, and I want to use the additive inverse properties. I haven't read, they were listed above, but I also copied them here. We already figured out that the additive inverse means the same as opposite, right? Just to be clear, so that's the same as opposite. We know when we take opposite twice, we're back at the same number, because imagine starting with A, reflecting it across 0 once, and then doing that again, so you're back at A, right? And now the opposite to the sum, so if you imagine going A and then B units backwards, so that's, let's say that's A and that's B, so that would be minus this total distance would be here minus A plus minus B, right? Then that would be the same if you walked A units forward and then B units forward, which then this one stands for A plus B, but then, so you're here, but then take its opposite and you're back at the same you were originally. So going A and B units backwards, this is the same as going the same A units, B units forward, and then taking its opposite, then reflecting across 0. So another thing for us, we can think of distributing minus among the sum, if you think about it that way. Okay. So let's find the opposite additive inverse of each of the following. So we want to find the additive inverse of this. So I want to find minus 3 plus x. Right? I want to find additive inverse of the given expression. We know that two additive inverses kind of cancel each other out, so that's gonna give me 3 plus x. Now I want to find additive inverse of A plus negative 4. So here this minus I will distribute, so minus A plus minus negative 4. But then again, I know that minus 4 will be 4. And here we want to find additive, again inverse, which is opposite of this given thing. Again, I'm going to distribute this minus, right? And that's going to give me 3 plus x. Okay.